Half a day! My name is Felix Gong and I am from the beautiful tropical island of Guam. I'm 16 years old and I'm participating in this year's Asia Pacific Conference of Young Scientists. Let's get on to the project! The title of my project is An Organic Alternative to Fossil Fuels, the Feasibility of Cocos nucifera oil as a Biodiesel. Introduction. Fuel is an energy source that is crucial for both industrial and suburban operations, but due to a variety of factors such as fossil fuel depletion and the international energy crisis, biofuels have been increasingly researched. At the current rate of consumption, which is over 4 million tons per year, crude oil reserves will run out in a mere 50 years. Additionally, the extensive use of fossil fuels has resulted in an increased release of greenhouse gases such as carbon monoxide, carbon dioxide, nitrogen monoxide, and sulfur dioxide. These chemicals result in phenomena such as acid rain, global warming, and can even result in a variety of human health issues. These detrimental consequences forces us to find an organic, more environmentally friendly alternative. One such alternative is the use of biofuels. What are biofuels? Biofuels are chains of fatty acid methyl ester derived from biomass. While fossil fuels are non-renewable, an organic source would be. Additionally, biofuels can reduce the release of greenhouse gases and also help aid the world with the international energy crisis. To produce these biofuels, a process known as transesterification is used. Transesterification can extract the methyl esters from the given triglycerides to form biofuel. This is then mixed with commercial diesel to form biodiesels, which is the topic of this project. To abbreviate the percentage of biodiesel in the mixture, the letter B is followed by the percentage of biodiesel. For example, B15 would consist of 15% biofuel and 85% diesel. As seen in the graph attached below, there is an increase in demand for biofuel internationally. In a tropical environment such as Guam, biodiesel extracted from Cocos nucifera or coconut should be considered, as research suggests that coconut oil can be used in traditional diesel engines without serious modifications. Previously cited studies show that coconut oil solidifies at 24 degrees Celsius or less, which is ideal in diesel engines. Additionally, the high cetane number of coconut oil, 51, enables it to ignite quickly and is within the cetane number range of diesel. Moreover, coconut oil can be burned without leaving significant residue, which is important to prevent clogging in engines. These factors are a result of the chemical makeup of coconut oil. Coconut oil is made up of fatty acids, including caprylic acid, capric acid, lauric acid, etc. Objective. The goal of this project was to determine the feasibility of coconut oil as a potential biodiesel. To test compatibility, 6 solutions with different blends of copra biodiesel were made: diesel, B5, B10, B15, B30, B100. After transesterification, the solutions were tested in a bomb calorimeter to test the total heat energy output of these blends. Lastly, a preliminary test of coconut biodiesel's viscosity was run to measure the effect of coconut biodiesel on the viscosity of the mixture. A high viscosity would increase fuel spray penetration and decrease overall fuel atomization, which would result in ring thickening and engine caulking. This would significantly reduce the efficiency of the engine. Hence, viscosity is also an important factor to test. On the screen now are my hypotheses. The first hypothesis predicted that the yield of the transesterification process will be less than 10%, as my research showed that most vegetable oil and other experiments showed a yield around 10 to 20%. My second hypothesis predicted that pure diesel would have the optimal thermal energy output, and the thermal energy output will be inversely proportional to the concentration of the biodiesel. Lastly, I predicted that the concentration of biodiesel will be directly proportional to the viscosity, as coconut oil has a pretty high viscosity. Materials. The materials I used are micropipettes, micropipette tips, beakers, potassium hydroxide, methanol, a blender, separating funnel, heat plate, water, pan, plastic wrap, dropper, benzoic acid, fuse wires, electronic thermometer, bomb calorimeter, timer, coconut oil, and diesel. Methods. The first part of the project is transesterification. The transesterification process has three solutions: the pre-treatment, the transesterification, and the post-treatment. In the pre-treatment, a mixture of potassium methoxide was used. To form this chemical from potassium hydroxide and methanol, 1 gram of potassium hydroxide was added to 15 grams of methanol and stirred for 5 minutes. After this chemical was safely poured into a blender, 100 grams of coconut oil at 40 degrees Celsius was added to the potassium methoxide, and the solution was blended at low speed for 120 minutes. Then, the solution was poured into a separating funnel to begin the transesterification step, and left to settle for 24 hours to allow for the separation of the glycerol and biodiesel layers. The glycerol was then carefully decanted from the biodiesel layer. The post-treatment step consists of washing the procured biofuel and distilling it. The biofuel was washed with water to eliminate the chemicals, and a simple distillation at 100 degrees Celsius was done to ensure the purity of the biofuel. The biofuel yield was recorded. Lastly, different mixtures of biodiesel were formed by mixing at different increments: pure diesel, B5, B10, B15, B30, and B100. The procedure was repeated for 3 times. Next is the bomb calorimeter test. All solutions were tested in the bomb calorimeter. The bomb calorimeter model was PAR 1341. According to the manual that was found on the PAR website, the solutions were tested and the data was collected. To do this, 1 gram of each solution was measured and placed into the solution dish. A fuse wire was connected to the chamber, just contacting the solution. The chamber was then charged with 30 times oxygen and placed into a 2-liter water container. After temperature stabilized, the sample was combusted. The temperature was recorded for every 30 seconds until the temperatures were consecutive, indicating equilibrium. The mass of the solution and the wires were also measured and recorded. The benzoic acid test was performed to calculate the calorimeter constant, which is the amount of heat energy absorbed by the calorimeter itself. The equation shown was used to calculate energy output. The last test was the viscosity test. Due to coronavirus restrictions, a proper kinematic viscosity test was not able to be done. However, a preliminary viscosity test was conducted to determine the effect that coconut biodiesel has on the viscosity of commercial diesel. To perform this experiment, a flat, long metal pan was measured and marked at the 25 centimeter mark. A smooth plastic wrap was wrapped around the pan. Then, the solution was dripped down using a dropper from the top edge of the pan, and the time it took to cross the line was recorded. The procedure was performed for all samples. Results. The project's goal was to determine the feasibility of coconut oil as a potential biodiesel source through a variety of factors, as mentioned before. The first factor is biodiesel yield. From the first part of the experiment, the production of biofuel from coconut oil was performed. As a result of the entire transesterification process, with the incorporation of potassium methoxide to lyse the cellular integrity of the coconut oil, the final yield as a percentage of the inputted coconut oil was 13.01%, as seen in the last row of the table. This is slightly lower than commercial production of some biodiesel from crops, but ultimately this number is very comparable. The reason why this is lower could be due to the equipment used and the concentration of potassium methoxide. The next tested factor was energy output. From the results of the bomb calorimeter experiment, it was found that the B15 solution produced the most thermal energy out of all the solutions. The data forms a negative parabolic shape with the peak of the energy production at B15, as seen in graph 1. The B15 solution produced about 90.5587 more joules than the 100% diesel. This is quite a large difference, considering that the solution was only 1 gram in volume. The last factor that was tested for is viscosity. Even though the viscosity test was not conducted under normal laboratory procedures, a preliminary comparison test of viscosities among the different blends was conducted, and the results were conclusive. As seen in Table 3, pure coconut oil has a high viscosity compared to the other solutions. However, the produced biodiesel was significantly less viscous than pure coconut oil. Despite the positive proportionality between viscosity and biofuel percentage, the increase is not that significant, which would mean that the mixture is suitable for engine use. However, the testing procedures for this particular experiment could result in some potential errors, as the cling of the plastic wrap as well as the slope of the pan could affect the overall measurement of viscosity. Conclusions. The first hypothesis was accurate, as a final yield of 13.01% was achieved, which is close to 10%. However, my second hypothesis was inaccurate, as the B15 solution actually produced more thermal energy than the commercial diesel. This could be due to the fatty acid structure of the coconut, as mentioned before. The last hypothesis was accurate, as the viscosity did increase with the increase in biofuel concentration. However, the increase was not large, and the solutions would still be safe for engine use. Some future expansions on this project would be the following. When situations permit, kinematic viscosity can be measured by the use of a kinematic viscosity tester found in the laboratory. Additionally, a gas chromatography test could be conducted to ensure the quality of the biodiesel produced. Additionally, other ASTM fuel standards can be tested, such as the water and sediment test, sulfated ash test, copper strip corrosion test, etc. However, these tests could not be conducted in this experiment, as coronavirus restrictions prevented it so. To conclude, the procured data indicates that biofuel derived from coconut oil is a potential biofuel source that should be further studied. I would like to acknowledge Dr. Vuki, Mr. Zhang Kyung-shin, Mrs. Carla Wong, and Mrs. Lopez for assisting me with this project. And here are the references that I used for my research and images. Thank you so much for watching my presentation, and please stay safe during these unprecedented times. Bye-bye!